Welcome to Quietly Made. I am so glad you have found your way here tonight. This is a space for the curious and the weary, a place where we explore the vast, invisible infrastructures of our world, while giving your mind the permission it needs to simply rest. Before we begin, I invite you to join our community by subscribing and leaving a comment. I often wonder where these stories find you tonight. If you feel inclined, please leave a comment sharing what part of the world you are in and the hour you are settling into sleep. It is a small way for us to feel the quiet connection of this community, scattered across different time zones, but sharing this same moment of rest. If you fall asleep, that is exactly what should happen. You are safe here. You can always come back tomorrow and pick up exactly where you left off. Adjust your pillow. Take a deep, slow breath in and let it out. Let your mind drift as we begin. Tonight, we turn our attention to the quiet assembly of the power grid, to the hum that lives in the walls of every building, to the copper threading through cities like veins through tissue, to the engineers who learn to tame lightning and send it coursing through wire at the speed of thought. This is not a story of sudden illumination. It is a story of incremental understanding, of coils wound by hand, of insulation that cracked and failed, of currents that killed before they were understood. It is a story written in the language of electromagnetic fields and resistance, in the buzz of transformers and the silent flow of electrons through metal. We begin not with light, but with a question that puzzled minds for generations. What is this force that jumps between objects, that makes hair stand on end, that sleeps in amber until awakened by friction? Electricity existed long before it had a name. The ancients observed it in the spark that leaped from finger to doorknob on dry winter days. They watched lightning split the sky and wondered if the gods were speaking. But observation is not understanding. The spark remained a curiosity, a parlor trick, a phenomenon without application. The shift began with those who refused to accept mystery as an answer. They built devices to generate static charge, wheels of sulfur that could be rubbed to produce sparks, glass jars that could store the charge, releasing it all at once in a snap of blue light. These were not tools, but instruments of inquiry, ways to ask the question, what are we dealing with here? The charge they generated was fickle. It dissipated quickly. It required constant generation. You could not store it for long, could not transport it, could not make it do useful work. But you could study it. You could measure how it behaved when confined to different materials, how it jumped across gaps, how it moved through water or metal or air. Some materials conducted it readily, others resisted. This was the first practical insight, that substances had different relationships with this invisible force. Metals allowed it to flow. Glass, rubber, ceramic stopped it cold. Between these extremes lay a spectrum of partial conductors, materials that permitted flow but impeded it, heating up in the process. This heating was not incidental. It was a clue. The force moving through wire was doing something, expending energy, transforming into heat. If it could become heat, perhaps it could become other things, motion, light, work. The challenge was making it continuous. Static electricity came in bursts, unpredictable and short-lived. What was needed was a steady flow, a current that did not exhaust itself, but could be maintained as long as necessary. The answer came from chemistry. Certain metals, when placed in certain solutions, produced a voltage difference. Connect them with a wire, and current flowed. Not a spark, but a stream. Not a momentary discharge, but a persistent circuit. These early batteries were crude assemblies of metal plates and acid, zinc and copper separated by brine-soaked cloth. The voltage was low, the current was weak, but it was steady, and steadiness meant possibility. Experimenters built larger batteries, stacking cells in series to increase voltage, connecting them in parallel to boost current. They discovered that the size of the plates mattered, that the concentration of the solution mattered, that temperature affected performance. Each variable was explored, documented, optimized. With reliable current came new experiments. Wire wrapped around iron created magnets. Current through a thin filament produced heat, sometimes light. Currents moving in loops generated forces that could produce motion. The principles of electromagnetism began to reveal themselves, not all at once, but through patient observation. The relationship between electricity and magnetism was subtle. A magnet near a wire carrying current would deflect. A wire loop rotating in a magnetic field would generate current. The two phenomena were intertwined, aspects of a single underlying reality. This realization opened pathways. If motion could generate electricity, then mechanical energy could be converted. A wheel turned by water or steam could spin coils in a magnetic field, producing continuous current without chemical batteries. The generator was born from this understanding. Early generators were inefficient devices. Heavy iron cores wrapped with miles of copper wire. The magnetic fields they produced were weak. The current they generated was inconsistent, pulsing rather than flowing smoothly. But they worked, and what works can be improved. Engineers experimented with different configurations. They tried permanent magnets, then electromagnets. They varied the number of coils, the thickness of wire, the speed of rotation. Each change altered the output, and each alteration taught them something about the relationship between mechanical input and electrical output. The current produced by these early generators alternated direction. As the coil rotated, it moved through magnetic fields of opposite polarity, causing the current to reverse with each half-turn. This alternating current was initially seen as a flaw, a complication that needed correction. Some inventors added devices called commutators, mechanical switches that reversed the connection at precisely the moment the current reversed, producing a pulsing direct current instead. Others wondered if the alternation itself might be useful, if there was a way to work with it rather than against it. The debate that followed was not merely technical. It was philosophical, economic, political. Different systems implied different infrastructures. Direct current could be stored in batteries. could be used to charge metal in electroplating, operated in ways that were familiar. Alternating current was stranger, harder to control, but it had properties that would prove essential for transmitting power over distance. At the heart of the matter was voltage. Electric current flowing through wire encountered resistance, and resistance generated heat. The thicker the wire, the lower the resistance. But thick wire was expensive, heavy, difficult to string between poles or bury underground. Thin wire was cheaper, but lost more energy to heat. The solution was to increase voltage. Power, the rate of energy transfer, is the product of voltage and current. The same amount of power could be transmitted at high voltage and low current as at low voltage and high current. But high voltage with low current meant less heat loss in the wire, much less. Alternating current made this possible through a device called the transformer. Two coils of wire wound around an iron core, not touching, but electromagnetically linked. Current alternating in one coil induced current in the other. The ratio of turns in the coils determined the voltage ratio. More turns in the secondary coil meant higher voltage output. Fewer turns meant lower voltage. This was elegant, almost too elegant. A simple device with no moving parts could step voltage up for transmission, then step it back down for use. Direct current had no equivalent. To change voltage with direct current required complex, inefficient machinery. The infrastructure implications were enormous. With transformers, power could be generated at one voltage, stepped up for transmission, sent across miles of thin wire, then stepped down at the destination for safe use. A single generating station could serve an entire region. But high voltage was dangerous, lethal. A shock from household voltage could startle or burn. A shock from transmission voltage could stop a heart instantly. The same property that made long-distance transmission economical made the infrastructure hazardous to anyone who touched it. Insulation became critical. Wire had to be coated, wrapped in materials that prevented current from escaping. Glass, ceramic, rubber, each had advantages and limitations. Glass was brittle. Ceramic cracked under thermal stress. Rubber degraded in sunlight and ozone. The insulators used on transmission lines were massive ceramic structures, shaped like bells or discs, stacked in series to provide sufficient insulation for voltages measured in thousands or hundreds of thousands of volts. They hung from cross arms on wooden or steel poles, holding the wire away from the structure, preventing contact. Even air served as insulation, but only if the gap was wide enough. High voltage could jump across air gaps, creating arcs of plasma that hissed and crackled. The higher the voltage, the wider the gap required. Transmission lines carrying extremely high voltage had to be spaced far apart, supported on towers that lifted them well above ground. The towers themselves were structures of calculated minimalism. Steel latticework, just strong enough to support the weight of the wire and withstand wind loads. The wire, thick strands of aluminum wrapped around a steel core for strength, hung in catenary curves between towers, sagging under their own weight. Installing these lines required crews to work at heights, stringing wire between towers that might be a quarter-mile apart. The wire came on huge spools, weighing tons. It had to be pulled through pulleys, tensioned precisely, secured to insulators with careful attention to prevent later failure. The geometry of the system was deliberate. 3 wires, not 2. 3-phase alternating current, a configuration where 3 separate currents oscillate out of step with each other, each reaching its peak at a different moment. This arrangement smoothed the power delivery, reduced the need for massive conductors, made the system more efficient. Generators were designed to produce 3-phase current. Transformers were built to handle it. Motors were wound to use it. The entire infrastructure, from generation to consumption, was optimized around this 3-phase system. At the generating station, turbines spun day and night. Some were driven by falling water, massive wheels installed in dams, turned by the weight and pressure of reservoirs. Others were driven by steam, produced by burning coal or oil or gas, or by the heat from nuclear reactions. The principle was the same regardless of the energy source. Create steam, direct it against turbine blades, extract rotational energy. The turbines were precision machines, their blades shaped to extract maximum energy from the steam flow. They spun at speeds measured in thousands of revolutions per minute, coupled to generators through gearboxes or direct drive systems. The generators themselves were immense, coils weighing tons, spinning inside magnetic fields produced by electromagnets, drawing thousands of amperes. The magnetic fields had to be controlled, kept uniform, prevented from distorting. The coils had to be cooled, often with oil or hydrogen gas circulating through channels in the windings. The electricity produced was sent to a switchyard, a field of transformers and circuit breakers where voltage was stepped up for transmission. The equipment in a switchyard operated at voltages that made the air itself glow if humidity was high. Insulators stood like forests of ceramic mushrooms. Conductors hung from elaborate support structures, spaced according to calculations that balanced cost against the risk of flashover. Circuit breakers protected the system. When a fault occurred, a tree falling on a line, a lightning strike, a failed insulator, current surged. Without protection, this surge could damage generators, start fires, cause cascading failures across the grid. Circuit breakers detected the surge and opened the circuit, interrupting current flow in milliseconds. Breaking high voltage current is not simple. When contacts separate, an arc forms, a sustained plasma discharge that continues to conduct current. The breaker must extinguish this arc quickly. Some designs blow compressed air across the arc. Others immerse the contacts in oil, where the arc vaporizes the oil, creating gases that blow the arc apart. The most advanced designs use vacuum, where there is nothing to ionize, no medium for the arc to sustain itself. The circuit breakers operated automatically, controlled by protective relays that monitored voltage, current, frequency. These relays were calibrated to distinguish between normal fluctuations and fault conditions. Too sensitive, and they would trip unnecessarily, interrupting service without cause. Too insensitive, and they would fail to protect equipment from damage. Finding the right balance required understanding the system's behavior under every conceivable condition. Engineers modeled the grid mathematically, calculating fault currents, analyzing transient responses, simulating scenarios. They tested equipment in laboratories, subjecting circuit breakers to currents that would vaporize ordinary conductors, verifying that the devices could interrupt the flow before damage occurred. Transmission lines carried power across landscapes, threading through forests, over mountains, across rivers. The routes they followed were planned with care. Straight lines were ideal, but rarely possible. Property boundaries, terrain, environmental concerns all influenced the path. Surveyors mapped potential routes, identifying obstacles, calculating distances. Engineers assessed each route's technical feasibility, estimating construction costs, evaluating maintenance access. Regulatory bodies reviewed proposals, weighing the utility's needs against landowner rights, against environmental impacts, against aesthetic concerns. Once a route was approved, construction began. Access roads were cut to tower sites. Foundations were excavated, often in remote locations where bringing in concrete and steel required ingenuity. Helicopters lifted materials to mountaintops. Temporary bridges crossed ravines. The towers were assembled on site, piece by piece, bolted together from sections small enough to transport. Crews worked with precision, aligning bolt holes, tightening connections to specified torques. The structures had to withstand not just the weight of the wire, but also wind loads, ice accumulation, seismic forces. Once towers were erected, wire was strung. This process required coordination across miles. A pilot line, a lighter cable, was pulled through first, sometimes using drones or helicopters. Then this pilot line pulled successively heavier cables until finally the conductor itself was hauled into position. The wire had to be tensioned correctly. Too loose, and it would sag excessively, risking contact with vegetation or structures below. Too tight, and it would stress the towers, risk breaking in cold weather when metal contracted. Tables and calculations specified the correct tension for each span, accounting for temperature, wire properties, span length. Splices joined sections of wire, creating continuous runs miles long. The splices had to be as strong as the wire itself, had to conduct electricity with minimal resistance, had to withstand the same environmental stresses. Crimped sleeves compressed around the wire, or compression fittings clamped the strands together, creating junctions that would last decades. At substations, voltage was stepped down for distribution. These facilities were smaller than generating stations, but no less complex. Transformers dominated, massive oil-filled tanks with bushings protruding from the top, connections to high-voltage lines above, and medium-voltage distribution lines below. The transformers hummed, a constant 60-cycle drone, the sound of alternating magnetic fields expanding and contracting in the iron core. The hum was louder when the transformer was loaded, quieter during periods of low demand. Maintenance workers learned to listen to this hum, detecting anomalies that might indicate developing problems. Inside the transformer, insulating oil served multiple purposes. It prevented electrical breakdown between windings. It transferred heat from the core to the tank walls, where cooling fins radiated it to the air. It preserved the paper insulation wrapped around the conductors, keeping moisture away, preventing degradation. The oil had to be kept clean, free of moisture and contaminants. Water in the oil reduced its insulating properties, increased the risk of flashover. Particles of metal or carbon, products of arcing or decomposition, had to be filtered out. Regular oil sampling and testing monitored the transformer's health, detecting problems before they caused failure. Failures, when they occurred, were often spectacular. A transformer failure could release thousands of gallons of burning oil, creating a fireball that required special firefighting techniques. For this reason, transformers were often surrounded by containment walls designed to hold spilled oil to prevent it from spreading. From the substation, distribution lines fanned out, carrying power into neighborhoods. These lines operated at lower voltages than transmission lines, but were still dangerous, still required insulation and careful spacing. They ran on wooden poles or were buried underground in conduits. The choice between overhead and underground was driven by economics, reliability, aesthetics. Overhead lines were cheaper to install and easier to repair. Underground lines were protected from weather, from vehicle collisions, from visual impact, but they were expensive, difficult to access, vulnerable to flooding. The poles that carried distribution lines were treated wood, resistant to rot and insects. They stood in rows along streets, supporting not just electrical wires, but also telephone lines, cable television, fiber optics. The utility space became cluttered, a tangle of cables at different heights, managed by different companies, each with their own requirements. Transformers hung from the poles, smaller versions of the substation transformers, stepping voltage down again for residential use. These distribution transformers served clusters of homes, their capacity matched to expected load. A quiet suburban street might need only a small transformer. A commercial district required larger units, sometimes multiple transformers working in parallel. The transformer's connection to each home was through a service drop, wires running from the pole to a weatherhead on the building, then down to a meter and main panel. The meter measured consumption, the spinning disc or digital display tracking kilowatt hours, the currency of electrical billing. Inside the building, the main panel distributed power to circuits. Each circuit was protected by a fuse or circuit breaker, devices that would interrupt current if it exceeded safe levels. The wiring followed codes, regulations developed over decades, written in response to fires and electrocutions, refined as new materials and methods emerged. Copper wire threaded through walls, insulated with thermoplastic or rubber, color-coded to indicate function. Black or red for hot conductors, white for neutral, green or bare for ground. The ground wire was a safety measure, providing a path for fault current, ensuring that if insulation failed and a conductor touched a metal enclosure, the current would flow to ground rather than through a person who touched the enclosure. The principles were simple. Keep current-carrying conductors insulated. provide a separate ground path. Size wire appropriately for the load. Use overcurrent protection. But implementation required attention to detail, careful workmanship, adherence to standards. Electricians learned their craft through apprenticeships, working alongside experienced practitioners, learning not just the code requirements, but the practical knowledge the codes could not fully capture. How to fish wire through walls without damaging it. How to make connections that would remain secure for decades. How to test circuits to verify that what had been built would function safely. The grid, as it expanded, became more than the sum of its parts. It became a network, interconnected, where power could flow along multiple paths, where generation in one region could serve demand in another. This interconnection improved reliability. If one generator failed, others could pick up the load. If one transmission line went down, power could reroute through alternate paths. But interconnection also introduced complexity. The grid became a dynamic system, constantly balancing generation and consumption. Power could not be stored in significant quantities. What was generated had to be consumed immediately. If generation exceeded demand, frequency would rise. If demand exceeded generation, frequency would fall. Maintaining stable frequency was essential. Motors, clocks, many devices depended on the 60-cycle rhythm of the alternating current. Deviations from this frequency indicated imbalance, signaled stress in the system. Control centers monitored frequency constantly, adjusting generation to match load, ensuring that the system remained stable. This balancing act occurred in real time. Demand fluctuated throughout the day, rising in the morning as people woke, peaking in the afternoon or evening, falling at night. Generation had to track this demand, ramping up or down as needed. Some generators could adjust output quickly. Hydroelectric turbines could change power levels in seconds, opening or closing gates to control water flow. Natural gas turbines could ramp up or down relatively quickly. Coal plants were slower, requiring time to adjust fuel feed rates to heat or cool. Nuclear plants operated best at steady output, their reactivity controlled by mechanisms that did not respond well to frequent changes. The grid operators matched generator capabilities to demand patterns. Baseload plants, nuclear, coal, some hydro, ran continuously, providing steady power. Peaking plants, natural gas turbines, pumped storage hydro, ran during high demand periods, filling gaps when baseload was insufficient. During periods of low demand, some generators might be curtailed, their output reduced to prevent oversupply. During peak demand, every available generator might be running at full capacity, and still the system might be stressed, voltages sagging, frequency dropping, operators issuing appeals for conservation. Energy storage offered a way to decouple generation from consumption, but large-scale storage was challenging. Batteries existed, but were expensive, their capacity limited. Pumped storage hydroelectric systems used excess power to pump water uphill into reservoirs, then released it through turbines when power was needed. This was effective, but required specific geography, 2 reservoirs at different elevations. Other storage concepts were explored. Compressed air energy storage, where air was pumped into underground caverns during low demand periods and released through turbines during peaks. Flywheels, massive rotating wheels that stored energy as rotational inertia. Thermal storage, where excess power heated materials that retained the heat for later use. Each approach had limitations, capital costs, efficiency losses, geographical requirements, technological maturity. The grid operated largely without significant storage, relying instead on the diversity of generation sources and the ability to forecast demand with increasing accuracy. Weather forecasting became integral to grid operation. Hot weather increased air conditioning load. Cold weather increased heating load. Cloud cover affected solar generation. Wind patterns affected wind turbines. Operators used weather forecasts to predict demand, to schedule generation, to prepare for stress events. Demand response programs paid large consumers to reduce usage during peak periods. Industrial facilities might shift operations to off-peak hours. Commercial buildings might pre-cool before peak times, then reduce air conditioning during the peak. These programs provided virtual capacity, reducing demand rather than increasing supply. The physical infrastructure required maintenance. Transmission lines developed problems. Insulators cracked, connectors corroded, conductors frayed. Vegetation grew, encroaching on clearances. Ice accumulated in winter, adding weight that stressed towers. Inspection crews patrolled the lines, sometimes on foot, sometimes in helicopters, looking for signs of trouble. They carried binoculars, cameras, thermal imaging devices. Hotspots indicated poor connections, areas of high resistance generating heat. Corona discharge, ionization of air around conductors, indicated sharp points or damaged strands. Repairs required taking equipment out of service, temporarily rerouting power through alternate paths. This could only be done when the system had spare capacity, when weather was favorable, when alternate paths could handle the additional load. Outages were scheduled months in advance, coordinated across utilities, planned to minimize impact. Some maintenance could be performed on energized lines, workers wearing conductive suits that brought them to the same electrical potential as the conductor. They accessed the lines from helicopters or insulated booms, working with tools designed for high-voltage environments. The work was hazardous, requiring extensive training, strict safety protocols, constant vigilance. Underground cables required different maintenance approaches. They could not be visually inspected. Problems were detected through electrical testing, through monitoring for partial discharges or insulation degradation. When a cable failed, locating the fault required specialized equipment, sensors that could pinpoint the location of the break or short. Repairs to underground cables involved excavation, splicing, testing. The work was disruptive, requiring street closures, sometimes affecting multiple customers for extended periods. For critical circuits, redundant cables provided backup, allowing one to be taken out of service for maintenance while others carried the load. The grid's reliability was measured in nines. 3 nines, 99.9% uptime, meant about 9 hours of outage per year. 4 nines meant less than an hour. 5 nines meant just over 5 minutes. Achieving high reliability required investment in redundancy, in maintenance, in advanced monitoring and control systems. Some customers required extremely high reliability. Hospitals, data centers, manufacturing facilities with processes that could not tolerate interruption. These customers often installed backup generation, diesel or natural gas generators that would start automatically if grid power failed, providing continuity until grid power was restored. The generators had to be maintained, tested regularly, fueled. They were expensive to own and operate, but for critical applications, the cost was justified by the value of avoiding downtime. The environmental impact of power generation could not be ignored. Burning fossil fuels released emissions, carbon dioxide, sulfur oxides, nitrogen oxides, particulates. These affected air quality, contributed to climate change, required controls and mitigation. Scrubbers removed sulfur from exhaust gases. Catalytic converters reduced nitrogen oxides. Electrostatic precipitators captured particulates. These systems were complex, expensive to install and operate, but necessary to meet environmental regulations. Nuclear plants produced no airborne emissions, but generated radioactive waste, material that remained hazardous for thousands of years. Storing this waste safely required containment systems designed to last longer than any human civilization had yet endured. The challenge was as much political as technical, with communities resisting the siting of waste storage facilities, with debates over permanent versus temporary solutions. Renewable sources, wind, solar, hydro, produced no emissions during operation, but they had their own impacts. Dams altered river ecosystems, affected fish migration, changed sediment transport. Wind turbines affected bird and bat populations, generated noise, altered landscapes. Solar farms required large land areas, sometimes displacing agriculture or natural habitats. Balancing these impacts against the need for reliable, affordable power was a continuing challenge. Engineers could design systems, economists could calculate costs, but the decisions were ultimately societal, involving trade-offs between competing values, between immediate needs and long-term consequences. Solar power converted sunlight directly into electricity through photovoltaic cells. The cells were made from silicon, doped with impurities to create regions of excess and deficit electrons. When light struck the cell, it freed electrons, creating current flow. The efficiency of early cells was low. Only a small fraction of sunlight was converted to electricity, but efficiency improved over time through better materials, better cell designs, better manufacturing processes. Cells became cheaper as production scaled, as competition increased, as technology matured. Solar panels, arrays of cells wired together, could be installed on rooftops, in fields, even floating on water bodies. They generated power during daylight hours, their output varying with sun angle, cloud cover, atmospheric clarity. On a clear day at noon, output was maximum. At sunrise or sunset, it was minimal. At night, it was zero. This variability posed challenges for grid integration. Solar generation did not match demand patterns. Peak solar production often occurred midday, while peak demand might be early evening. Storage or complementary generation was needed to bridge the gap. Inverters converted the direct current produced by solar panels into alternating current compatible with the grid. The inverters had to synchronize with grid frequency, had to regulate voltage, had to disconnect if grid power failed to prevent backfeeding power into lines that workers might assume were de-energized. Grid-connected solar installations became common on residential and commercial buildings. Owners generated some or all of their electricity, sometimes feeding excess back to the grid. Utilities had to adapt, implementing net metering programs, upgrading distribution systems to handle bidirectional power flow, managing the intermittency introduced by thousands of small generators. Wind turbines converted the kinetic energy of moving air into electricity. The turbines stood on towers, their blades sweeping circles hundreds of feet in diameter. The blades were shaped like aircraft wings, their cross-section designed to generate lift, causing them to rotate when wind struck them. The rotational speed was controlled, kept within limits to prevent damage. In high winds, blades could be pitched to reduce their angle of attack, shedding excess energy. In extremely high winds, turbines were shut down entirely, the blades feathered to minimize loads. The rotation drove a generator, sometimes through a gearbox that increased rotational speed to match generator requirements. The generator produced alternating current, typically at variable frequency, due to fluctuating wind speeds. Electronics converted this to direct current, then inverted it back to alternating current at grid frequency. Wind farms consisted of dozens or hundreds of turbines spread across hilltops or plains or offshore waters. The spacing between turbines mattered. Too close, and they interfered with each other. Downstream turbines receiving turbulent, reduced energy air. Too far apart, and land use efficiency decreased. Wind was even more variable than sunlight. It could shift in minutes. Forecasting wind required sophisticated meteorological models, consideration of local terrain effects, analysis of historical patterns. Errors in forecasting affected grid operations, requiring backup generation to be available when wind output fell short of predictions. Offshore wind farms accessed stronger, more consistent winds, but faced harsh marine environments. Turbines had to resist salt corrosion, wave loads, extreme weather. Installation required specialized vessels, pile driving or floating foundations, underwater cable connections to shore. The cables themselves presented challenges. Underwater cables for high voltage DC transmission were used to connect offshore wind farms to the grid. DC avoided the issues of capacitance and inductance that limited the length of AC underwater cables. Converter stations at each end transformed between AC and DC, adding cost but enabling transmission over distances that AC could not achieve. Hydroelectric generation used the potential energy of water at elevation, converting it to kinetic energy as water fell, then extracting that energy with turbines. The principle was ancient, but the scale and sophistication of modern installations were not. Large dams created reservoirs, storing water that could be released as needed. The height of the dam and the volume of water determined potential energy. Penstocks, large pipes, carried water from the reservoir to turbines at the base of the dam. The water's velocity at the turbine was substantial, driven by the pressure of the water column above. Turbine designs varied. Pelton wheels used water jets, striking cups on the wheel's periphery. Francis turbines used water flowing radially inward through curved blades. Kaplan turbines used propeller-like blades, adjustable to optimize efficiency across varying flow rates. The turbines spun generators, producing electricity with efficiency exceeding 90%. Hydroelectric generation could ramp up or down quickly, adjusting to grid demands by controlling water flow. This made hydro valuable for balancing the grid, for responding to fluctuations in supply or demand. Run-of-river hydro installations use flowing rivers without large reservoirs. They generated power based on current flow, which varied seasonally, daily. They had less environmental impact than large dams, but also less flexibility in generation scheduling. Pumped storage used two reservoirs at different elevations. During low demand periods, excess grid power pumped water to the upper reservoir. During high demand, water was released back through turbines, generating power. The round-trip efficiency was around 70 to 80%, meaning some energy was lost. But the ability to store energy and release it when needed provided significant grid benefits. Nuclear power generated electricity through heat from controlled nuclear fission. Uranium atoms split when struck by neutrons, releasing energy and more neutrons. These neutrons could split additional atoms, sustaining a chain reaction. Control rods absorbed neutrons, regulating the reaction rate. The heat produced boiled water or heated a separate coolant, creating steam. The steam drove turbines connected to generators, just as in fossil fuel plants. The nuclear reactor replaced the boiler, but the rest of the power generation process was similar. The advantage was energy density. A small amount of nuclear fuel could produce as much energy as millions of tons of coal. A nuclear plant could operate for months on a single fuel load, generating steady power without air emissions. The challenges were complexity and risk. Nuclear reactions produced radioactive byproducts, some with half-lives measured in thousands of years. The reactor had to be contained, shielded, cooled continuously even after shutdown. Safety systems were redundant, designed to prevent accidents, to mitigate consequences if prevention failed. Accidents, when they occurred, had severe consequences. Reactor core damage could release radioactive material into the environment, contaminating areas for decades. The possibility, however remote, shaped public perception, regulatory requirements, industry practices. Reactor designs evolved toward inherent safety, where physical properties, rather than active systems, prevented runaway reactions. Passive cooling systems that functioned without power or human intervention. Fuel designs that could not melt down. But public skepticism remained, shaped by past incidents, by concerns about waste disposal, by fears that were sometimes rational and sometimes not. Fossil fuel plants, coal, natural gas, oil, remained the backbone of generation in many regions. They were well understood, relatively inexpensive to build, capable of running whenever fuel was available. Coal plants pulverized coal into fine powder, blowing it into boilers where it burned, heating water to create steam. The steam drove turbines, then was condensed back to water and returned to the boiler. The efficiency of this process, the fraction of fuel energy converted to electricity, was around 30 to 40%. The rest became waste heat, dissipated through cooling towers or discharged into water bodies. Natural gas plants used turbines similar to jet engines. Gas burned in a combustion chamber, the hot exhaust driving turbine blades. The turbine's rotation generated electricity. Exhaust heat could be recovered in combined cycle plants, used to produce steam for a second turbine, increasing overall efficiency to above 50%. Gas turbines could start quickly, ramp up or down rapidly, making them ideal for peaking generation. They were cleaner than coal, producing less carbon dioxide per unit of energy, no sulfur, less particulate. But they still relied on a fossil fuel, still contributed to climate concerns. Oil was less commonly used, typically reserved for backup generation or remote locations where other fuels were impractical. It was more expensive, produced more emissions than natural gas, but was liquid and easy to store. The fuel supply chain for fossil plants was itself an infrastructure. Coal came from mines, transported by rail or barge to plants, stockpiled in massive piles. The plants consumed thousands of tons per day. Ensuring uninterrupted supply required contracts, logistics, contingency planning. Natural gas flowed through pipelines, a network parallel to the electric grid. Compressor stations maintained pressure, storage facilities provided buffer capacity. Gas supply could be interrupted by pipeline failures, by extreme weather, by supply disruptions. Plants maintained some on-site storage, but it was limited. Oil was delivered by tanker truck or rail car, stored in tanks near the plant. The storage provided days or weeks of fuel, depending on tank size and consumption rate. Fuel costs dominated operating expenses. When fuel prices rose, electricity prices followed. When fuel was cheap, electricity was affordable. The economics of generation shifted with fuel markets, influencing which plants operated, which sat idle. The grid's evolution continued, driven by changing demands, new technologies, policy decisions. Distributed generation, rooftop solar, small wind, combined heat and power systems shifted power production closer to consumption. This reduced transmission losses, provided resilience during grid outages, but complicated grid management. Microgrids emerged, localized grids capable of operating independently from the main grid. They served campuses, military bases, remote communities. They could disconnect during grid disturbances, maintaining power locally while the larger grid recovered. Electric vehicles introduced new demand patterns. Millions of cars plugged in to charge, drawing power from the grid. If charging was uncontrolled, it could stress the grid during peak hours. But if managed, charging delayed to off-peak periods, or even feeding power back during peaks, vehicles could help balance the grid. Smart meters replaced mechanical meters, providing real-time data on consumption. Utilities could track load patterns in detail, identify inefficiencies, detect theft. Customers could see their usage, adjust behavior to reduce costs. Time of use pricing encouraged shifting consumption to off-peak periods, smoothing demand curves. The grid became instrumented, sensors monitoring voltage, current, frequency at thousands of points. Data flowed to control centers, where operators monitored dashboards, received alerts, coordinated responses to disturbances. Automation increased. Switches and breakers that once required manual operation were motorized, controllable remotely. Fault detection systems automatically isolated problems, rerouted power, minimized outage duration. Self-healing grid concepts emerged, where the system could automatically reconfigure to restore service after disruptions. But automation also introduced vulnerabilities. Cyber attacks could target control systems, potentially causing widespread outages. Utilities invested in cybersecurity, implementing protections, monitoring for intrusions, developing response plans. The threat was real, evidenced by incidents where malicious actors had compromised utility systems, though most intrusions were detected and mitigated before causing damage. The grid's physical security was also a concern. Substations, transmission towers, and generating plants were potential targets. Fences, cameras, guards provided some protection. But the infrastructure was vast, distributed, impossible to secure completely. Redundancy and resilience were the primary defenses, designing the system so that the loss of any single component would not cause widespread failure. Critical facilities had enhanced security. Nuclear plants operated under strict regulations, with armed guards, multiple barriers, surveillance systems. Key substations in urban areas were hardened, their components protected, their locations sometimes unmarked to avoid drawing attention. Natural disasters posed risks that security measures could not prevent. Hurricanes damaged transmission lines, flooded substations. Earthquakes toppled towers, ruptured gas lines. Wildfires burned through corridors where transmission lines ran. Ice storms coated lines with inches of ice, collapsing structures under the weight. Recovery from major events required mobilizing crews from across regions, coordinating repairs, prioritizing critical services. Hospitals, water treatment plants, emergency services received power first. Residential areas followed. The process could take days or weeks, testing the patience of those without power, the endurance of those working to restore it. The people who kept the grid running worked in shifts, around the clock. Control room operators monitored screens, communicated with field crews, made decisions that affected millions. They trained for years, learning the intricacies of the system, practicing responses to scenarios, building the judgment needed to act under pressure. Line workers climbed poles, worked in trenches, operated boom trucks. They wore protective gear, followed safety procedures, looked out for each other. The work was dangerous. Electrocution, falls, vehicle accidents claimed lives. Training emphasized safety, but the risks could not be eliminated. Maintenance crews tested equipment, replaced aging components, performed upgrades. They worked from detailed schedules, following procedures developed over decades. Precision mattered. A bolt torqued incorrectly could lead to a failure months later. A test performed sloppily could miss a developing problem. engineers designed new systems, planned expansions, analyzed failures. They used software to model the grid, to simulate faults, to optimize configurations. They reviewed incident reports, identified root causes, recommended changes. Their work was often invisible, noticed only when something went wrong. Planners looked years ahead, forecasting demand growth, identifying where new generation or transmission would be needed. They balanced technical requirements against economic constraints, against regulatory mandates, against public opposition. Their projections shaped investment decisions, determined where resources would be allocated. Regulators set standards, approved rate increases, mediated disputes. They held hearings, reviewed filings, issued orders. Their role was to balance utility interests against consumer protection, to ensure reliability while keeping costs reasonable. The electricity bill that arrived each month was the visible face of this vast infrastructure. A few numbers: kilowatt hours consumed, rate per kilowatt hour, total cost. Behind these numbers were thousands of people, millions of components, decades of accumulated knowledge. Most consumers never thought about the grid. They flipped switches, plugged in devices, expected power to be there. And usually it was. The reliability was so high that outages were notable events, disruptions to the normal state of affairs. This expectation of reliability was a testament to the engineers and operators, to the infrastructure they had built and maintained. But it was also a vulnerability. When outages did occur, people were often unprepared, lacking the skills or resources to cope without electricity. Electricity had become essential, not just for convenience, but for survival. Heating, cooling, refrigeration, medical equipment, communication, all depended on power. A prolonged outage could be life-threatening, particularly for vulnerable populations. Utilities recognized this dependence, worked to maintain reliability, communicated with customers during outages. But the fundamental fact remained: the grid was complex, aging in places, stressed by increasing demand and changing generation patterns. Maintaining it required continuous investment, constant vigilance. Aging infrastructure was a persistent challenge. Equipment installed decades ago was reaching the end of its design life. Transformers from the mid-20th century were still in service, their insulation degrading, their cooling systems less efficient. Transmission towers showed signs of corrosion, their steel thinning, their foundations settling. Replacing this equipment was expensive. Utilities had to balance the cost of replacement against the risk of failure. Condition assessment techniques, thermal imaging, ultrasound, oil analysis, helped identify equipment most in need of replacement. But assessment was imperfect. Failures sometimes occurred in equipment that seemed healthy. The regulatory environment affected replacement decisions. Rate structures that rewarded capital investment encouraged upgrades. Those that did not left utilities reluctant to spend. Regulators had to approve major expenditures, weighing the need against the impact on customer rates. Customers, for their part, wanted reliable power at low cost. These goals sometimes conflicted. Reliability required investment. Investment increased costs. Finding the acceptable balance was a political as much as a technical process. Demand was changing. Energy efficiency improvements, LED lighting, better insulation, efficient appliances, reduced per capita consumption in some regions, but population growth, increasing use of air conditioning, proliferation of electronic devices countered these gains. Overall demand continued to rise, though more slowly than in past decades. Electric vehicles represented a significant future load. If adoption reached projected levels, millions of vehicles charging daily could increase residential demand by significant percentages. Utilities planned for this, upgrading distribution transformers, reinforcing circuits, implementing managed charging programs. But the timing and magnitude of EV adoption were uncertain. Projections varied widely. Utilities had to plan for a range of scenarios, balancing the risk of overbuilding against the risk of being unprepared. Electrification of heating, replacing natural gas furnaces and water heaters with electric heat pumps, represented another potential demand increase. Heat pumps were efficient, but they still drew power, especially during cold weather, when heating loads were highest. Winter peak demand, traditionally lower than summer in many regions, could shift. These changes would affect the grid's load profile, the pattern of demand throughout the day and year. Planning for these shifts required forecasting, modeling, scenario analysis. Errors in forecasting could result in capacity shortages or expensive overcapacity. Renewable integration continued to grow, driven by declining costs, policy mandates, corporate commitments. But integrating large amounts of variable generation posed technical challenges. Solar and wind generation varied with weather, not with demand. Sometimes they produced abundantly when demand was low. Other times they produced little when demand was high. Balancing the grid required flexibility from other generation sources, or storage, or demand response. Battery storage costs were declining, making utility-scale installations economically viable. Batteries could absorb excess renewable generation, discharge during periods of scarcity, provide grid services like frequency regulation. But batteries were still expensive, their capacity limited compared to demand. Pumped storage remained the largest source of grid-scale storage, but suitable sites were limited. Compressed air storage, thermal storage, and other alternatives were being explored, but none had achieved widespread deployment. Grid operators managed renewable variability by forecasting generation, maintaining reserves, coordinating with neighboring systems. Interconnections allowed renewable-rich regions to export power when generation exceeded local demand, import when it fell short. But interconnections had limits. Transmission capacity was finite. During periods of widespread low wind or solar, neighboring regions might also face shortfalls. Ensuring reliability required maintaining sufficient dispatchable generation, sources that could run whenever needed. Natural gas plants serve this role in many regions, providing the flexibility to ramp up when renewables underperformed. But reliance on gas raised questions about long-term sustainability, about whether the goal of decarbonization could be achieved while depending on fossil generation for reliability. Energy policy shaped the grid's evolution. Renewable energy standards mandated minimum percentages of generation from renewable sources. Carbon pricing or regulations limited emissions from fossil plants. Subsidies reduced the cost of renewable installations. Each policy intervention altered the economics of generation, influencing investment decisions. The policies were often contentious, debated in legislatures, challenged in courts, revised as political winds shifted. Utilities and generators advocated for favorable policies, opposed those that threatened their interests. Environmental groups pushed for aggressive action. Industry groups urged caution. Consumers were caught in the middle, their rates affected by policy choices, their access to reliable power dependent on decisions made by others. Public input was solicited through hearings and comment periods, but the technical complexity often limited meaningful engagement. The grid itself was indifferent to these debates. It operated according to physical laws, responding to changes in generation and load, regardless of the political context. Policy affected what was built, how it was operated, who paid for it. But the fundamental physics, the relationship between voltage, current, resistance, the behavior of electromagnetic fields, remained unchanged. Looking at a map of the grid revealed its geographic scope. Transmission lines crisscrossed continents, linking distant regions. In North America, 3 major grids, Eastern, Western, and Texas, operated largely independently, with limited interconnections between them. Each managed its own balance, its own reliability, its own challenges. Within each grid, regional organizations coordinated operations, planned transmission expansions, ensured compliance with reliability standards. These organizations brought together utilities, generators, and regulators, providing forums for collaboration and dispute resolution. International interconnections linked grids across borders. Power flowed between countries, traded in markets, allocated by agreements. These interconnections increased reliability, allowed sharing of resources, but also required coordination across jurisdictions with different regulations and priorities. The grid's operation was a continuous negotiation between supply and demand, between reliability and cost, between competing interests and values. It was managed by people making decisions, often under uncertainty, with incomplete information, facing constraints both technical and political. The physical presence of the grid was everywhere and nowhere. Wires overhead, cables underground, transformers on poles, substations behind fences. Most people walked past these components daily without noticing them, their attention directed elsewhere. But the grid shaped the landscape. Transmission corridors cut through forests, their paths cleared of tall vegetation. Substations occupied parcels in industrial areas or hidden behind screening. Power plants loomed on horizons, their cooling towers or smokestacks visible for miles. In cities, the grid was buried or camouflaged. Underground vaults held transformers and switches. Wires ran in conduits beneath streets. Building rooftops concealed equipment. The infrastructure blended into the urban fabric, present but unobtrusive. In rural areas, the grid was more visible. Lines strung between poles marched across fields and hills. The poles themselves became landmarks, navigation aids, elements of the rural aesthetic. Farmers worked around them, sometimes grateful for the power they carried, sometimes annoyed by the easements that restricted land use. The aesthetic impact of the grid was debated. Some saw beauty in the geometry of transmission towers, in the elegant curves of hanging cables, in the functional design of industrial equipment. Others saw blight, intrusions that marred natural landscapes, symbols of humanity's dominance over nature. Underground transmission lines eliminated visual impact, but increased costs by factors of 5 or 10. The trade-off was rarely worth it, except in sensitive areas, national parks, historic districts, affluent neighborhoods where residents had political influence. Wind and solar installations also affected landscapes. Wind farms were visible for miles, their turbines turning slowly, blinking lights marking their presence at night. Solar farms covered acres with reflective panels, transforming agricultural land or desert into industrial facilities. These visual impacts sparked opposition. Residents near proposed wind farms complained about noise, shadow flicker, aesthetic disruption. Solar projects faced similar resistance. The tension between local impacts and broader societal benefits, renewable energy, reduced emissions, played out in zoning hearings and permitting processes. The grid's relationship with water was significant. Thermoelectric plants, fossil and nuclear, required vast amounts of cooling water. They withdrew it from rivers, lakes or oceans, passed it through condensers to absorb heat, then returned it, warmed by several degrees. This thermal pollution affected aquatic ecosystems. Warmer water held less oxygen, stressed fish populations, altered species composition. Regulations limited temperature increases, sometimes requiring cooling towers instead of once-through cooling. Towers evaporated water to dissipate heat, reducing thermal discharge, but consuming water in the process. During droughts, water availability for cooling could limit plant operations. Reduced river flows or elevated ambient temperatures meant less cooling capacity, requiring plants to reduce output or shut down entirely. Hydroelectric generation depended on water but did not consume it. Water passed through turbines and returned to the river, but dams altered flow patterns, affecting downstream ecosystems, river temperatures, sediment transport. Fish migration was blocked or required fish ladders, structures that allowed fish to bypass dams, though with varying success. Conflicts between water use for power generation and other uses, agriculture, municipal supply, recreation, ecosystem health, were common. Water rights were complex, governed by laws that varied by jurisdiction, shaped by history and politics. The grid's carbon footprint was substantial. Electricity generation accounted for a significant fraction of global carbon dioxide emissions. Reducing this footprint required shifting from fossil fuels to low-carbon sources, renewables, nuclear, carbon capture and storage. Carbon capture technology, which removed CO2 from exhaust gases and sequestered it underground, was technically feasible but expensive and energy-intensive. It reduced the net power output of a plant, increased costs, required suitable geological formations for storage. Few plants had been retrofitted with carbon capture. New plants designed with it were rare. The economics did not favor it unless carbon was priced or regulated, and even then, renewables were often more cost-effective. Reducing grid emissions thus focused on replacing fossil generation with renewables or nuclear. But this transition was not simple. It required new transmission to connect remote renewable resources to load centers. It required storage or flexible generation to manage variability. It required investment in grid upgrades, in control systems, in workforce retraining. The pace of transition varied by region, driven by resource availability, policy commitments, economic conditions. Some regions moved quickly, achieving high renewable penetration. Others progressed slowly, constrained by cost, by reliance on existing fossil infrastructure, by political resistance. The social dimensions of the grid extended beyond environmental concerns. Access to electricity was a marker of development, a prerequisite for modern life. Regions without reliable power faced limitations in education, healthcare, economic opportunity. Electrification efforts in developing regions followed different paths than the grid's initial development in industrialized nations. Centralized generation and extensive transmission were expensive. Distributed generation, solar panels, small wind turbines, micro-hydro, offered alternatives, bringing power to remote villages without requiring connection to a grid. These off-grid systems had limitations. They provided less power, less reliability, but they were affordable, scalable, sufficient for basic needs: lighting, phone charging, refrigeration. As these systems proliferated, questions arose about whether to connect them to expanding grids or to develop them as independent microgrids. Connection provided access to more power, greater reliability, but it also meant dependence, vulnerability to grid outages, integration into regulatory and market structures that might not serve local interests. Energy justice became a concern in developed nations as well. Low-income households spent higher percentages of income on electricity, struggled to pay bills, faced disconnection. Efficiency programs helped but required upfront investment that many could not afford. Utilities walked a fine line. They had obligations to serve all customers, but also financial requirements to meet. Disconnecting non-paying customers was a last resort, but allowing non-payment threatened financial stability. Programs to assist struggling customers, payment plans, energy assistance, weatherization helped but did not eliminate the problem. Net metering, which credited rooftop solar owners for excess generation, raised equity questions. Solar installation required capital. Homeowners with good credit could finance systems. Renters, low-income households, those in multifamily buildings often could not. Yet all customers paid grid costs, while solar owners reduced their bills. Regulators grappled with these issues, seeking rate structures that were fair, that encouraged efficiency and renewable adoption, that ensured grid sustainability. Solutions were elusive. Every policy created winners and losers. Every change faced opposition from those adversely affected. Workforce challenges loomed. Many utility workers were nearing retirement, taking decades of knowledge and experience with them. Recruiting younger workers was difficult. The work was demanding, sometimes dangerous, often unglamorous. The skills required, electrical knowledge, mechanical aptitude, troubleshooting ability, were not common. Training programs, apprenticeships, partnerships with technical schools attempted to build the pipeline, but the transition was slow. The grid's increasing complexity required new skills: data analytics, cybersecurity, renewable integration, while still needing traditional expertise in power systems, electrical equipment, and field operations. The grid operated in the background of daily life, unnoticed until it failed. Then its importance became immediately, starkly clear. Lights went out, refrigerators stopped, furnaces quit, Communication networks went silent. The modern world, so dependent on electricity, faltered. Outages reminded people of their dependence, of the fragility underlying the reliability they took for granted. The food in the freezer began to thaw. Phones ran out of charge. Darkness fell without the flip of a switch to banish it. Utilities rushed to restore power, prioritizing critical services, working through the night. The public's patience varied. Some understood the challenges, appreciated the efforts. Others demanded immediate restoration, complained about response times, threatened legal action. The economics of outages were significant. Lost productivity, spoiled goods, disrupted services added up to billions in costs. Incentives existed to minimize outage duration, but the realities of repairs, locating faults, accessing damaged equipment, completing work safely, imposed limits on how quickly power could be restored. In the quiet hours before dawn, when demand was lowest, the grid hummed on. Generators spun at synchronized speeds, their outputs woven into a continent-spanning network. Transmission lines carried currents measured in thousands of amperes, their conductors warm from resistive heating. Transformers droned their steady 60-cycle song. In control rooms, operators watched screens, alert for anomalies. In substations, equipment functioned automatically, relays monitoring, breakers ready to trip if needed. In homes, appliances drew power, converting electrical energy into light, heat, motion, computation. The infrastructure that enabled this was vast. Miles of cable, acres of substations, forests of poles. It represented decades of investment, generations of accumulated knowledge, countless hours of labor. It was maintained by people who understood it, respected it, knew its dangers. They climbed towers in lightning storms. They worked on energized lines, their lives dependent on procedures and equipment. They made decisions affecting millions under pressure, with incomplete information. The grid they maintained was imperfect, aging in places, stressed in others, challenged by changing demands and generation patterns. But it worked. Most of the time, it worked. The grid was a human creation, reflecting human priorities, human limitations, human ingenuity. It was shaped by the desire for comfort, for convenience, for economic growth. It was constrained by physics, by economics, by the finite resources available. It served billions of people, most of whom never thought about it. They flipped switches and expected light. They plugged in devices and expected power. The grid delivered day after day, year after year, with a reliability that made it invisible. This invisibility was both success and vulnerability. Success because the grid worked so well that it could be taken for granted. Vulnerability because taken for granted systems receive less attention, less investment, less appreciation. The people who built and maintained the grid knew its importance. They saw the consequences when it failed. They understood the complexity, the constant balancing act, the thin margins between adequacy and shortage. And so they worked. In control rooms, monitoring flows. In the field, repairing lines. In offices, planning expansions. They kept the grid running, not for glory or recognition, but because it needed to be done. Electricity flows because of a difference in potential, a voltage gradient that drives current through conductors. It flows from generation to load, seeking balance, following the path of least resistance. It does not care about markets or policies, about equity or justice. It obeys physics. Yet the grid that carries it is profoundly human, built by human hands, operated by human minds, serving human needs. It embodies values, the belief that everyone should have access to power, that lights should turn on when switches are flipped, that the modern world should not be constrained by the limits of pre-industrial life. These values are not universal. They carry costs, environmental, economic, social. They require trade-offs, compromises, decisions about what matters most. Different societies make these decisions differently, shaping their grids to reflect their priorities. But everywhere, the fundamental challenge is the same: to generate electricity reliably, transmit it safely, deliver it affordably, while minimizing harm and maximizing benefit. The solutions vary, the challenge endures. As night deepens and you drift towards sleep, the grid continues its work. Somewhere, a turbine spins, a transformer hums, a circuit breaker stands ready, an operator watches a screen, a line worker drives to a fault location. The electricity flowing through wires in your walls came from generators miles or hundreds of miles away. It traveled through transmission lines, stepped down through transformers, distributed through circuits. It arrived in an instant, at the moment you needed it. This is the triumph of the grid, that it makes the complex simple, the distant near, the impossible routine, that it delivers power with such consistency that its absence, not its presence, is remarkable. The infrastructure that enables this is massive, intricate, fragile in places, robust in others. It is the product of more than a century of development, of lessons learned through failure, of incremental improvement. It will continue to evolve. New technologies will be integrated. Old equipment will be replaced. The balance between generation and load will shift. But the fundamental purpose will remain: to provide electricity reliably, safely, affordably. And in serving this purpose, the grid connects us all, not just electrically through wires and transformers, but through the shared dependence on the invisible force that powers modern life. We are all nodes in this network, drawing power, benefiting from its presence, affected by its failures. Good night. And so, the narrative of this assembly comes to its quiet conclusion. Whether you are still awake, or whether you have already drifted into a deep and peaceful sleep, know that you are exactly where you need to be. The world is vast, but tonight, its systems are simply the backdrop to your rest. Thank you for joining me here at Quietly Made. Rest now. Join us again tomorrow. Good night.